Today we will review some of the key ideas encountered in the first part of vectors. Our first concept is scalar multiplication. So if you are given a number or a scalar k, to multiply it to a vector, here we multiply it component-wise. I think most of us hopefully should find this pretty intuitive and straightforward to carry out. Another example in the IJK notation is shown here. More importantly than being able to carry it out is to understand what does scalar multiplication mean and when should we use scalar multiplication when we are encountering problems to solve. So this picture will explain what scalar multiplication is about. We usually visualize vectors as a directed line segment. So for example, let's have the vector A, we visualize it with this arrow over here in black. For the vector 2A, we are multiplying by 2. So what it means is we are scaling it by 2 times. So this blue arrow over here, it's 2 times as long as the one in black. So this represents 2A and is in the same direction. If you multiply a vector by a negative number, we are reversing the direction. So as shown in this example in red over here. So if you can observe the 3 vectors we have over here, we realize that these 3 vectors are parallel. And this gives us our first formula for this topic. So 2 vectors, A and B, are considered parallel if we can find a number k or a scalar k such that A is equals to k of B. So anytime we encounter parallel vectors, this formula is pretty useful for solving problems. Another use of this formula is to prove whether 2 vectors are parallel if we can find such a number k such that this formula will work out. Our next concept is vector addition. Similar to scalar multiplication, the mechanics, hopefully it's pretty intuitive and straightforward. Given 2 vectors, to add them up, we add them up component-wise. This is seen in this example in the column vector notation as well as in the IJK notation over here. To visualize what it means, there are 2 ways to actually visualize vector addition. So the first way is given 2 vectors A and B, as shown in this picture over here, we draw them directing outwards from a common point. We then construct a parallelogram, and the diagonal gives us the addition A plus B. Another way to visualize a vector addition is to construct them head to tail instead. When we do that, we form a triangle, and this third side of the triangle is our vector A plus B. Next, we would like to use the language of vectors to describe points. So we should have seen the idea of points and coordinates in our earlier study. So to convert them to vectors, what we do is we create a fixed point called the origin with coordinates 0, 0, 0. The vector OA then describes the vector starting from the origin and ending at the point A. This vector can be described in color vector form as shown over here. The next formula allows us to convert a vector, the vector from A to B, the vector AB, in terms of its position vectors. So AB is given by OB minus OA, the position vector of B, minus the position vector of A. So using our earlier concepts of vector addition and multiplication by -1, hopefully we can figure out why this formula is true. So this picture gives us a hint of what is going on. This seemingly simple formula is actually very useful in solving a whole assortment of questions because it allows us to convert between vectors AB to position vectors OB and OA and vice versa. We will see the use of this formula many times in the example at the end of this video. The next concept we have is to describe collinearity. So given 3 points A, B and C, they lie on the same line, we use the word collinear to represent that, if AB equals to K times of BC. So the reason for this formula is because if you look at this picture, the vector AB is parallel to the vector BC, and we have a formula from parallel vectors from earlier on. Of course, we are not restricted to using the numbers, the vectors AB or BC. We can use AC, CB, and all sorts of combinations of them. Next, we want to describe vector magnitude, or the length of a vector. This formula gives us the length of a vector. It's essentially the use of Pythagoras' theorem. If you are interested in how this is derived, I'll give a link in the comments below of how this formula can be derived from 2-dimensional Pythagoras theorem. Also, I will have a link to a blog post about why we use the modular symbol to describe the vector magnitude. The next concept is the concept of unit vectors. So this formula allows us to calculate how long or what's the magnitude of different vectors. If a vector's magnitude happen to be 1, we will call it a unit vector. So a vector B is called a unit vector if the magnitude of it is 1. So given a vector A, it need not necessarily be a unit vector. To convert it to the unit vector, we use scalar multiplication. We take A divided by its own magnitude so that its magnitude now becomes 1. we give it a special symbol, a hat, with a hat on top of the vector itself to represent that now this vector has been converted into a unit vector. So why do we want to talk about unit vectors and have formulas for it? An example of it is shown in this picture, or in this formula. So given a vector A that is 5 units long, we often would like to create a vector that is parallel to A that is 7 units long. The answer is not 7A, because 7A multiplies A by 7 times. So we're given something that is 5 units long, multiplying by 7 gives us something that's 35 units long. That's not what we want, or quite what we want. So instead, step 1, we change the vector A into its unit vector A hat, that's 1 unit long. Now given this unit vector, multiplying it by 7 gives us a vector parallel to A that is 7 units long. So if we want a vector that has magnitude k parallel to A, we use the formula ka hat. The next concept we're going to discuss is ratio theorem. So this theorem allows us to calculate the position vector of a point in the middle of two other points A and B, as long as we know the ratio between the AC and CB. So the theorem goes this way: if C is between A and B such that AC is to CB is lambda is to mu, the ratio theorem gives us this formula. Thankfully, this formula is given to us in the formula booklet, and we can just plug and use it whenever we want. If you're interested, you can give a try to derive this formula using concepts of parallel vectors. So personally, how I remember this formula is to get the vector in the middle, OC, we do cross multiplication. We take lambda multiplied by OB plus mu multiplied by OA over lambda plus mu. Our last concept is useful for more abstract kind of questions. So some questions we are given that A equals to 5i plus 3j, for example, and we can proceed to do calculations using the numbers 5, I, and 3j. However, for some more abstract questions, we have less tools to work with. In that case, we have this concept of comparing vectors. So given two vectors, if they are non-parallel, A and B, and we form an equation that Ka plus Lb equals to Ma plus Nb. So in such a case, K will be equals to M, the coefficient of A in a sense, and L will be equals to N. This is similar to the concepts of comparing coefficients we may have seen earlier in the study of polynomials and surds. So these are the main concepts encountered in the first part of vectors. In the next video, we will encounter the concepts of scalar and vector products, or the dot and cross products for vectors. But before we wrap up the video, we will look at an example question to take a look at how the concepts we have just discussed can be used in solving questions. So let's take a look at this specific example. Consider a triangle ABC and let CA equals to P and CB equals to Q, where P and Q are non-parallel. So we have this vector CA is given by the vector QP, and CB is given by Q. So for this question, C at the start is behaving like the origin for us. Next, let X, Y, and Z denote the midpoints of AB, AC, and BC respectively. So as shown in this picture. For part A, we let D denote the point of intersection between AZ and BY. We want to find the vector CD in terms of P and Q. So let's try it out. So to tackle this question, we start by using the fact that Y and Z are the midpoints. So we know that CA is the vector P, so CY will be half of P. Similarly, CZ will be half Q. Our objective for this question is to eventually find the vector CD, where D is the intersection between AZ and BY. Since it's the intersection, it makes sense to try to find the vectors AZ and BY first. So let's try to find what AZ is. To figure it out, we will use our position vector formula. Recall that AZ is OZ minus OA. But for this question, we will, for now, use C as if it's the origin. So AZ is given by CZ minus CA. CZ we have found is half Q, while CA is the vector P. Next, we find the vector BY. Similarly, BY is given by CY minus CB. CY we found is half P, while CB is Q. So D is the intersection between these two lines. Which of the concepts that we have discussed earlier on can be used to proceed with this question? There are a few ways you can decide to use ratio theorem. That's one possible way to tackle this question. But for this example over here, I'm going to use the concept of collinearity. Notice that B, D, and Y are collinear. So we can use the formula to arrive at BD. It's a multiple of BY. In particular, BD equals to the multiple, I'm going to call it lambda, of BY. So we'll use the position vector formula again. BD is given by CD minus CB equals to lambda of BY. BY we have found to be half P minus half Q. Upon simplification, we get the fact that CD equals to CB, which is CB is Q. Q plus lambda half P minus Q. Let's group all the P's and Q's together. So we equals to lambda over 2P plus, this is 1, this is minus lambda Q, plus 1 minus lambda of Q. Okay, now let's proceed with the same strategy, not for BY, but now for AZ. A, D, and Z are collinear. So AD, it's a multiple of AZ. So we have AD equals to, I'm going to call the constant mu of AZ. Using our position vector formula again, AD is CD minus CA equals to mu of AZ. AZ we found to be half Q minus P. Let's make CD the subject. CD equals to CA. CA is P. So we have P plus mu half Q minus P. Expanding and grouping all the P's and Q's together, we have 1 minus mu of P plus mu over 2 of Q. So we have two different ways to write CD. CD can be written as lambda over 2P plus 1 minus lambda Q. CD can also be written as 1 minus mu of P plus mu over 2 of Q. This means that we can equate these two expressions together. So we have lambda over 2 of P plus 1 minus lambda of Q is equal to 1 minus mu of P plus mu over 2 of Q. We are told that P and Q are non-parallel, so we can compare. Comparing P, we have lambda over 2 equals to 1 minus mu. So cross multiply the 2 across, we have lambda equals to 1 minus mu. Let's now compare Q. We have 1 minus lambda equals to mu over 2. Okay, let's sub in what lambda is. 1 minus 2, 1 minus mu equals to mu over 2. We expand. 1 minus 2 plus 2 mu equals to mu over 2. Let's find out what mu is. Bringing mu over, you get 3 mu over 2. Bringing these two guys over here, we get 1. So mu is 2/3. Okay, now let's plug mu is 2/3 into our expression for CD. So CD is given by 1 minus mu of P plus mu over 2 of Q, which simplifies to be 1/3 P plus 1/3 Q. And this answers the first part of the question. So for the second part of the question, for part B, we have, if we let the position vectors of A, B, and C with respect to an origin O be A, B, and C respectively, find the position vectors of D in terms of A, B, and C. So now O is introduced into our question. Let's give it a try. So now we are doing part B. Now that O is introduced in our equation, we can use our position vector formula once more. The formula that CD is equals to OD minus OC. So CD is given by OD minus OC equals to 1/3 P plus 1/3 Q. For this part of the question, we want to express everything in terms of A and B. So we need to figure out what P and Q are. So let's simplify. OD minus OC is given by the vector C equals to 1/3. P is given by CA. And Q is given by CB. As I mentioned earlier, the position vector formula is really useful. So let's plug it in again. 1/3. CA is A minus C. And CB is B minus C. Okay, so simplifications, OD equals to C plus, expand, we get 1/3 A minus 1/3 C plus 1/3 B minus 1/3 C. So our final answer, 1/3 A plus 1/3 B. Here we have C minus 1/3 C minus 1/3 C, which gives us plus 1/3 C. And this is our final answer. So now that we've solved the question, let's take a look at the question back again to try to understand what we've just done. So in this question, we have found the intersection between AZ and BY. If you're interested, you can actually try to find the intersection between these lines and CX, and it turns out the three lines actually meet at a common point. So this is a pretty interesting behavior that works for all triangles, and we call this point the centroid of a triangle. And let's look at our answer. Our final answer for what OD is, this centroid of the triangle. OD is 1/3 A plus 1/3 B plus 1/3 C. This is pretty interesting if you think about it. When we have 2 points, A and B, how do we find the midpoint of A and B? We take half A and half B. Now that we have 3 points forming a triangle, how do we find this idea of a center of a triangle? We have our formula, our answer, 1/3 A plus 1/3 B plus 1/3 C. Pretty fascinating, isn't it? So this wraps up this video. In the next video, we will talk about the dot and cross products.